Is it visible to everyone?
Yes, sir.
Okay. Welcome all of you. So today I would like to discuss about the mechanical properties of some materials, on materials, MEMS materials, because we have to recapitulate the previous means what you have taught in you have read in first year. So mechanical and some electrical properties, how these properties can be affected on MEMS material. Mm, so I would like to discuss about some of these points or some definitions relating to the mechanical properties. Okay, so now the Poisson's ratio, which is another important parameter that is required for the analysis of the mechanical or the stress strain analysis of silicon for mechanical microsensor. That's why it is required. Okay, so last day uh, I have given the brief idea about or the basic terms related to the mechanical properties like stress strain. These are discussed. So Poisson's ratio, that is important to analysis the micro devices or MEMS devices. Okay. So this Poisson's ratio, when an external tensile stress is applied, the diameter decreases. Okay, with an application of the axial compressive stress, the diameter increases. So when I define the axial, then I told you that the diameter is not changed, only on the length changed. Last day I have discussed, but in real it is not the fact. Okay, so if you elongate a body, diameter will be same. Okay, is not it? That is actual reality. So there the diameter decreases if you apply tensile strain for uh, if you apply compressive stress, then the diameter will be increases. Okay, clear. So diameter decreases if you apply tensile strain, and diameter increases if you apply the compressive stress. So the axial strain, which is here, it is given by this epsilon a, that is the del L by L. Okay, so the difference of the length divided by actual length, that is the axial strain. And here the transverse strain, that is the epsilon t, which is the change of diameter divided by d. Okay, so Poisson's ratio, actually, that is the epsilon t divided by epsilon a. That means the transverse strain divided by axial strain. Okay, that is called the Poisson's ratio. Now basically strength means we are applying stress. So when you are working for certain sensor, you have to be cautious. So you should not apply stress, so that the yield strength or tensile strength, last day I have discussed yield strength and or tensile strength, it reaches. So yield strength is higher, that is the preferred knowledge. Okay, uh, so that you can use maximum amount of stress. So we look for a material whose yield strength is higher. If you noticed in the last day slide, so if the material whose yield strength is higher, that is to be very useful, okay, to calculate the maximum amount of stress. Now the yield and tensile strength, that is sigma y yield strength, and sigma t, that is the tensile strength. Okay, so yield strength is the stress above which the material will permanently deform, and that is called the plastic deformation. Okay, and the tensile strength where that is mm, the stress above which the material will completely break. That is the tensile strength. Okay, so yield strength is the stress above which the material will permanently deform into plastic. So plastic deformation is called the yield strength, and tensile strength is the stress above which the material will completely break. And according to these criteria, so here, if the tensile strength is greater than yield strength, then the material bends before breaks, which is called the ductile. Okay, and if the tensile strength that is comparable, okay, with the yield strength, then the material breaks, which is called the brittle. So ductile or brittle, these two words are used in this case. Now, what do you mean by ductile? Ductile is sigma t, when sigma t is greater, uh, large compared to the sigma y, then the material bends before break, and so this property is known as a ductile property. On the other hand, when sigma t and sigma y are comparable, then material breaks and is a brittle material. We call it maximum point of the shear stress. Okay. So these are the mechanical properties which you should know before going to the design of any micro mechanical structures. Okay. Other Now other mechanical properties are also important, like when you go for design any MEMS based device, okay, or microsensor device. Now these are the thermal expansion, hardness. Okay, so thermal expansion, what is thermal expansion? So thermal expansion actually occurs when an object expands and become larger due to a change in the object's temperature. Now, to understand how this happened, we need to think about what temperature actually is. Temperature is nothing but average kinetic energy of the molecules in a substance. So, a high temperature means that the molecules are moving faster. Uh, Average, it is moving faster. If you heat up material, the molecules move faster, and as a result, they take up more space. They tend to move into areas that were previously empty. Okay, now this causes the size of the object to increase. Okay, so that is the thermal expansion. Now thermal expansion coefficient is known as alpha. It is basically delta L by L by K. K is basically the temperature in absolute scale. Okay, so it is defined percent change in length per unit K. So that is thermal expansion coefficient. You should know it. It results in thermal stresses due to mismatch in alpha between different materials. So you see thermal stress, earlier stresses we discussed, which is mechanical stress. So that we are applying certain mechanical force, and as a result of that force means the stress. So strain will be developed inside the material after that. And so another stress is also there, that is the thermal stress. That means in a sensor you are not going to make a sensor using only single material, and you are using different kinds of materials, semiconductors, ceramic, metal, and so on, etc. So all the materials will not have the same thermal expansion coefficient. So if the temperature changes, the operation uh, the operation will be altered, and because you are using sensor not in a fixed temperature, at different temperatures ranges you are using the same sensor, so that the temperature range, the thermal expansion coefficient is not same, and as a result of which there will be a stress, and that stress is known as thermal stress. Okay, and because of that stress, some of the sensor behavior or sensor output may also change. So that also you have to keep in mind. uh, so other than the mechanical stress, there is another stress which is involved, which is called as thermal stress. Okay, next is the hardness. So hardness is another mechanical property. Physical hardness of a material characterized by a Knoop hardness constant. You can check it from the website. What is Knoop hardness constant? I will not discuss this thing. Knoop hardness constant. Okay, it's a testing method uh, for hardness calculation. Okay, and it is in kg per millimeter square. So Loop is basically is a name of a scientist. Okay, he investigated that particular property of that material. That is why it is characterized by Knoop hardness, and it is defined by kg per millimeter square. That is the unit. Okay, so it's a one type of testing method which is called the Knoop hardness constant testing. Now other different properties are also available, like creep. Okay, so creep and fatigue. So these are all mechanical properties. So what is creep? Creep is basically time dependent and permanent deformation of materials when subjected to a constant load and stress below or close to the yield strength. Okay, so it occurs at elevated temperature and static stress. If temperature is elevated and static stress is applied, then this is known as the creeping. And other property which is known as the fatigue. Uh, so change in material properties caused by cyclic loads at stresses much lower than the yield strength. That means you are applying stress lower than the yield strength. But if you are applying cyclic stress, that means one, you are applying stress and then release it, again you are applying stress then release it, and again you are applying stress then release it. So in this way, the cyclic order, the stresses can be applied. So that's why it is called cyclic stress. So in a cyclic way, if you apply stress and then release, then the material property, that particular mechanical property of the material will little bit change, and that is known as fatigue. Okay, if the material reached its fatigue condition, it may not follow the linear stress strain relation. So that's why it is fatigue. So these are various kinds of mechanical properties. The axial stress, the shear stress, and yield strength, that brittle, ductile, creeping, fatigue. These are various kinds of mechanical properties. Once you take care of uh, this, when you are going for a design of any microstructure using silicon material, or any other single crystal, or even using the metal or metal alloys, like I have said earlier, different materials can be used: silicon, metal, metal alloys. Okay. So silicon is a mechanical material. So our main focused in including this material is the silicon substrate. Okay, because everything in like most of the thing, not everything, most of the devices are based on the
Hello,
silicon material.
sorry sir for joining late. I just joined.
Yes,
Have I missed anything, sir?
yes, but I have to upload these things on YouTube. You can easily go through these slides we have,
Okay, okay,
which
okay,
you
sir.
have missed. Okay, right now you have to mute yourself. Okay.
Okay, okay.
So so our main concern is silicon, which is the substrate material on which we can perform any pattern to make it a device, means based device. Any sensor can be made using the silicon. Okay, so maximum time we can use the silicon. material. So silicon is a mechanical material and which is having single crystal, and it has got a diamond crystal structure. Okay, so its density we have seen is equal to aluminum, nearly equal to aluminum, but one third of the steel. So in their respect, the silicon is lighter than steel. Okay, in a second point, it's hardness. So hardness is half of the steel and greater than iron or tungsten or aluminum. Okay. Mm, Next is the thermal expansion coefficient. Thermal expansion coefficient, uh, which is 1/5 of the steel. So there is a good thing that in thermal expansion, and coefficient is not very hard in case of silicon. Okay, so here is a silicon structure with 8 atoms per unit cell. So it's like cubic structure. So now other properties are yield strength, which is 2 times greater than the steel. Young's modulus is almost equal to the steel. Thermal conductivity, that is 1.5 times of steel, and deform elastically. And remember, not plastically, elastically. Okay, there are two terms related to this deformation. One is the elasticity, and plasticity or plastically. So it's not the plastic, it is elastically deformed, and it has no hysteresis. So silicon and its derivatives, particularly silicon dioxide or silicon nitride, are some of the best electrically characterized materials in the world. So in different MEMS structure, we take help of these derivatives of silicon, that is silicon nitride and silicon dioxide, and their properties and their characteristics are well known to us. So that's why this that is one of the advantages in case of silicon, and that's why silicon is preferred. So other things are mentioned here in favor of silicon, that is why silicon for micromechanics or microsensor or MEMS. So here are the points. um, it has got excellent mechanical performance, and it enables effectively to replace a majority of all other sensing technologies. Okay, the existing infrastructure of the mainstream IC industry is available, so that we will use in case of MEMS fabrication or microsensors fabrication. So that is how it is very easy to develop products which offer an unmatched price to performance ratio. The performance will be very good and price will be low. That is the main aim. Okay, so the ratio of price to performance is extremely low in case of silicon because of the available of the infrastructure, which is very important. If you have to create a new infrastructure, then obviously the price to performance ratio will be higher and higher. So since it is available, so that the ratio will be extremely low, that is advantageous for commercial production purpose. Okay, so that is one advantage in case of silicon. The other one is based on with this particular thing is based on known characterization of silicon. It can be classified as the best material for mechanical sensor. Okay, silicon mechanical strength is comparable comparable to even higher than the steel, but at a lower density and better thermal conductivity. Okay, uh, so in the last slide I have showed you its density is lower than iron. Okay, here, so its density is and better and lower, and its thermal conductivity is also very high compared to 1.5, this one. So because of that, it cannot generate lot of heat. So a lot of heat distribution is more, and that is advantageous compared to other materials. So that is our desired thing. So these are the favorable points in case of silicons. Okay. Other properties like here also the lack of mechanical and thermal hysteresis and uh, so that hysteresis is not desirable property of any of the sensor material. Now silicon, uh, mechanical and thermal both hysteresis are extremely low. There is another hysteresis, that is a thermal hysteresis. Because change of property with thermal energy, where the thermal energy is withdrawn, so it will retains its original property, so that it is the so thermal hysteresis criteria and mechanical also we have so if you apply some mechanical pressure or stress or strain, so then property will change. If you release the stress and strain, you will get back its original property, so that it is known mechanical hysteresis. So those things are not desired things if you choose to material for making any case any kind of sensor. So that is why silicon is one material that is the strong material or making the for making the mm, micro sensor, because it does not have either mechanical hysteresis or it does not have any thermal hysteresis. Okay. Other point is high sensitivity to stress and the piezo resistive effect in silicon. As a, it has a stress sensitivity to orders of magnitude larger than that of the metal strain gauge, which enables fabrication of high output devices with simple electronics. Okay, so that that means it is highly sensitive to stress because it has got very good piezoresistive property. Okay, that means its resistance will change in the application of pressure. Okay, other points are next point is the batch manufacturability. Mm, that is the batch production, the capability of manufacturing completed mechanical structure simultaneously on multiple wafers, each carrying multiple devices. So at a time, large number of productions can be can be performed. Okay, that is called the batch processing. Uh, so that also reduces the price. And other than those points, a few other advantages points are in case of silicon is access to ultra pure material. That means you can get very good quality, very pure silicon material because it is used in various sites. Uh, like I have said earlier, last day 100111010 in this type. Okay, so automatically that technology is established, you can get ultra pure silicon material access to advanced semiconductor process, and no needs of discussion, that is availability of the high volume package technologies. Okay. Uh, Although the packaging technologies are available for various sites, but in case of MEMS, the packaging will be little bit critical, and those critical points, how to circumvent those points, how to recover from those problems, there's still a lot of research is going on, and here some custom packages required which needs some R&D, research and development purpose also in case of MEMS and microsystem devices. Okay, so access to high volume manufacturing equipment and available base for educated silicon processing technologists. So that means the manpower is available. So manpower is the one basic thing when you go for any technological development, because you are going to use all the VLSI equipment. So trained manpower for running those equipment for VLSI processes already available. Okay, and those manpower can be used for making MEMS also, or any kind of microsystem production purpose. So that is why, since available manpower is there, so there is no extra investment for training the manpower, That is one advantage in case of silicon MEMS. So those points basically enable us to go ahead with silicon MEMS to get to a greater extent. Okay, that's why silicon is preferred, because it is already used in VLSI technique. Now, some mechanical properties of silicon I have discussed, and here, since we are going to use some thin films of semiconductor materials along with its derivative, means silicon dioxide or silicon nitride, etc. So some of the properties related to thin films are discussed here. In this case, there are two kinds of uh, stress. One is the extrinsic stress, another is the intrinsic stress. So what do you mean by intrinsic stress? Intrinsic stress means the stress which has developed inside the single crystal silicon during the growth process. Now, what are those? They may be due to the growth stress when you are growing the crystal. So during that time, lattice misfit, if there is a misfit between the crystal lattice points, a stress may be developed. Substitutional or interstitial impurities, they will create some stress. A volume changes by phase transformation when you grow the crystal. Because of that reason also stress may be developed, and then those all belong to the intrinsic stress. And what are the extrinsic stress? When all silicon, mm, this is the silicon substrate, you can see in this diagram, and this is the thin film, the upper position, there is the thin film, for example polyimide film. The polyimide film, you are depositing on the single crystal substance. Okay. Now you see, during deposition of this thin film over this substrate, in many cases the temperature may be increased. So it is maybe greater than the room temperature. So TD, that is the deposition temperature, and here the room temperature, which is it is TR. So now when during the position, in many cases the strain or stress may be developed at the inner phase, because if you go for deposition more than room temperature, then or even less than room temperature, very low temperature also can be used in both cases, both because of the uh, difference of the thermal expansion coefficient of the deposited film and the basic substrate. So there will be a mismatch between the expansion coefficient, and as a result of which a stress may be developed at the interface. Okay, so in this interface, this is the thin film and this is the substrate. In between here, stress may be developed. That is basically the extrinsic stress, and normally the TF means the film thickness we are going to deposit, its thickness is extremely low uh, compared to TS. Okay, substrate, this one, substrate thickness, it's very less. So because of that, also sometimes the stress will be developed at the interface between the deposited film and the silicon substrate. So now if alpha is a expansion coefficient of the film, and alpha A is a expansion coefficient, this is the for the substrate alpha S. It has been observed when alpha F means the expansion coefficient of the film is greater than the alpha S expansion coefficient of the substrate, then the developed stress is the tensile stress. Okay, and that example is the polyimide on the silicon. in this case, in this type of example, because alpha F in case of the polyamide, it is greater compared to the alpha S. So the tensile stress will be developed. On the other hand, if the film expansion, thermal expansion coefficient is less than the thermal expansion coefficient of the substrate, example is the silicon dioxide over silicon, then the stress developed is a compressive stress. So this is the two reason when the tensile will be produced, or when the compressive stress only produced. It depends on the thermal expansion coefficient of the deposited film and also the substrate. Okay, so these are the extrinsic stress and intrinsic stress, um, what I have told you. So those are sometimes responsible for some changes of the properties of the device, because if that are not matched, then what will happen, there is a deformation of the structure. Because of this, the inherent developed stress, which may be intrinsic or may be extrinsic due to mismatch. Okay, so please mute yourself, everyone. So now there is another thing is mentioned, which is also very important in case of the fabrication of the sensor, which involves a lot of deposition of the thin film. Okay, so adhesion, that is another property which we must look into, uh, because when you depositing many kinds of films on different kinds of substrates in this way. So this is the substrate, okay, and thin films, different kinds of thin films you need to deposit it over this substrate. So the addition between the film and the substrate will be very good. If it is not good, then in the subsequent process, those films may peel off. So in order to avoid that, we have to study the addition property of the film with the substrate. Okay, now here you see, because this is the film deposited on this substrate, and after the micro uh, machining, you have removed the substrate from the bottom. So now if we apply pressure, so then the pressure is applied on the film. That film may be silicon dioxide, maybe silicon nitride, or maybe a mechanical any type of another film, which may be polyamide film, whatever it is. Then if we apply pressure on the film, you see it is there is a chance of peeling off from the substrate. Okay, so there is a so this to prevent uh, that you need the addition of the film, and the substrate should be extremely good. So in that case, if you evenly apply pressure, then this portion of the film will not come out. Okay. Mm, so that is required, and in many cases during processing you can use the ultrasonic hesitation, or sometimes abrasion also used. uh, so those are mechanical energy you are applying to the substrate during the processing. That means during the ultrasonic vibration, or the film, when you apply the ultrasonic vibration, the film should not come out. That is another criteria. There are some cases of scotch tape test is being done, so to see how the addition is with the basic substrate. Okay, so then addition is another important property which we have to look into before finalizing a process tape for making films on substrate. different kinds of film and different kinds of substrate can be used. For example, the gold. If you want to deposit gold on silicon and silicon dioxide, it has been observed the addition of the gold is not very good with the silicon or silicon dioxide. In that case, sometimes it may be required to put an interfacial layer which will help addition of that deposited film with the substrate. In gold, we normally use the chromium because chromium helps addition of the gold film with the silicon substrate. Okay, so these are the mechanical properties of the material we need to consider before any type of design of any MEMS devices or any micro sensing devices. Okay, so that's all for today. If you have any queries, any doubts, you can ask me. Unmute yourself and you can ask me the question. Okay, so next day we will discuss about the electronic properties of on materials, because according to your syllabus there are some review of mechanical and some electrical properties which is in module 1. So we have to go through that module. It's a huge syllabus in MEMS and little more complicated than semiconductor devices. So if you have any queries, you can ask me. Do you have any queries?
No, sir.
Devanjana and Devarya.
Yes, sir.
Yes, sir.
Huh. You have joined very late, so there are already I think 7 classes are performed, and every lectures have been uploaded on YouTube. You can go through that lectures. I have given the lecture slides and the videos over the Google Classroom. You must go through that so that you can understand the later part. Okay. Otherwise,
Okay, sir. Okay.
you will not understand from this point. Okay, so what is MEMS, why it is used, what is the application, or which material, what is the process of making the devices using MEMS techniques, everything I have explained in a shorter way, because the certain terms that is related to the full syllabus. And in module, if according to the syllabus in different modules, certain positions are need to be discussed in more details. Okay, so detailed description will be later in later classes, but previously I have already given some brief introduction about the process, how the MEMS devices can be made, which materials can be considered,